All right, in this video, I'm going to talk about problem 6 from the 4C homework, which was problem 4.90. I've copied it here onto my whiteboard. It's a single gas molecule of inertia m is trapped in a box and travels back and forth with a constant speed v between opposite walls A and B, a distance L apart. At each collision with the wall, the molecule reverses direction without changing speed. Okay, interesting situation. And then the problem is write algebraic expressions for the magnitude of the change in momentum of the molecule as it collides with the wall B. All right, this, if you're reading this, is a really new kind of problem, not like any of the ones that we've been doing before. This is a totally kind of abstract kind of situation. And it may seem very foreign to you. Of the students that I've talked to already, it has seemed like a very foreign kind of problem. It seems like I don't even know where to begin. I don't understand what this is describing. It's all variables. There's no numbers. What the heck? And my response is, oh, I love this problem. This is like one of the first ones we've gotten to do where we're really thinking in the way that I remember from my undergraduate physics and from graduate school of like, just let's think about what's going on one molecule at a time and how that interacts with the rest of the world. So in the situation, we've got a box. It's a one-dimensional box because we're not thinking about the molecule going up and down and left and right and all of that. We're just imagining it's more like a tube. It's going left and right. We've got a molecule stuck in the center of the box. It's got an inertia of m trapped inside. It's traveling back and forth at a constant speed. Okay, so if it's the only molecule in there, it's not going to collide with other molecules. It's not going to change its speed because all of its collisions with the wall are going to be elastic. So it's just moving back and forth with the speed v, bouncing, going all the way back again, bouncing, going all the way back again, bouncing. Maybe this sounds sort of boring, but there's some cool things that are about to happen here. So we've got a length for the box. That's the distance from one side to the other. We've got side A, side B. Okay, at each collision with the wall, the molecule reverses direction without changing speed. So that's what I mean by an elastic collision. So this is really like a real gas molecule trapped inside a box. It's just that it's the only one. Okay. As we get through it, we're gonna reveal a bit more about what we're doing. So write algebraic expressions for the magnitude of the change in momentum of the molecule as it collides with the wall B. Okay. Well, it would be helpful for me to know what's the momentum of the molecule before it hits the wall. So we're over here at this wall. We've got the molecule about to hit. Let's zoom in on it. The molecule is about to hit. So we've got a momentum of P equals inertia of the molecule times the velocity of the molecule to the right. And then just after that collision, we're still zoomed in on that box, the molecule's going the other way now. Nothing else has changed. So in that situation, just afterwards, peak final is minus m times v, because it's now going to the left. So the change is going to be the final momentum minus the initial momentum. That's minus mv minus positive mv. So the change is minus 2mv as a vector. The question asks for the magnitude of that change. So for the magnitude of the change, we can drop the negative sign, and you get m times v. 2. Don't forget the 2. Correct. Yay. Okay. So one collision of that molecule with the wall changes the momentum by 2mv of the molecule. But we also know that that's the momentum change of the wall as well, because the wall changes by an equal and opposite amount to what the molecule does. So as the molecule changes by minus 2mv, the wall changes by plus 2mv. All right, write an algebraic expression for the amount of time between collisions with wall B. Okay, so now we're imagining The molecule has hit wall B, it turns around, it now goes all the way across the tube, hits the other wall, does exactly the same thing. It hits, changes momentum by 2 mv, turns around, going the same speed as before, and goes all the way back again. Okay, so we know how fast the molecule is going. It's going speed v. We know the distance that it travels between collisions. So from one collision to the next, it travels L all the way across, and then L all the way across again. So the distance is 2L. And we know the relationship between speed and distance and time. So distance equals rate times time. Distance equals rate times time. The distance is 2L. The rate is V. The T is the thing that we're trying to find. So divide that V over to the other side, and you get the time between collisions is 2L over V. So whatever the speed of that molecule is, whatever the size of the box, twice the length divided by the velocity gives you how much time it takes between each collision. All right, write an algebraic expression for the number of collisions per second the molecule makes with wall B. All right, let's think about this number that we just got. T is 2L over V. What are the units of that? If you write in the units of the length, that's meters, and of the velocity, that's meters per second. So if you simplify that, and you can treat units like variables, and I kid you not, this is how a lot of physics derivations work. You just kind of write down the units of things, and you kind of cancel them out, and that tells you something about the relationship between things. Meters, meters, seconds goes up on top. So the units of this is seconds. Okay, well, we knew that already. It's a time. But it's the seconds for what? What happens in that number of seconds? One collision happens. So I'm going to write this as it's the number of seconds per collision. So 2L over V is the number of seconds for each collision. The question I'm asking here is the number of collisions per second. I have seconds per collision. I want collisions per second. That strongly suggests that what I want to do is I want to reciprocal this thing. So I want collisions per second. And I have seconds per collision. So if I flip it over, I'll get that. So that's V over 2L is the number of collisions per second. So let's try that. V divided by 2L. Perfect. Okay, so isn't this wild? I've just got some information about the speed and the size of the box, and I already know how many collisions per second there's going to be. All right, here we get to it. What's the change in momentum undergone by wall B per second? Okay, well, in part A, I discovered that the momentum change for each collision was 2 mv. And in part C, I just discovered how many collisions per second there were. So I want delta P per second. How much is the momentum change each second? I have number of collisions per second. And I have the change in momentum per collision. This is almost like a stoichiometry problem from chemistry. You're just combining the units in a way to help you understand something. So I want momentum change per second. I have these things. I can cancel out the collisions part of it. and that will give me the delta P per second. So the way I combine these things is by putting those two expressions together. So the thing I want is going to be the number of collisions per second, V over 2L, times the momentum change per collision, which is 2mv. Let me fix that L. All right, so now let's simplify that expression. The 2's are going to cancel, and the v's will combine into 1, and you get mv squared over L. So mv squared divided by L. And we're done with the problem. But I want you to think a little bit about this expression that we got. This is the rate of change of momentum of the box due to one molecule bouncing back and forth. So this expression, if you've done some of your chapter 5 reading, you might recognize that mv squared, that's related to the kinetic energy of the molecule. And the L is related to the size, or to use more vocabulary that we've used before, extension of the box. So we have energy divided by size gives you how quickly the momentum of the box changes. One of the reasons I love this problem is because I remember this kind of thing, doing this a lot. And what you get out of this, if you think about it carefully, is a relationship between the energy of the things inside the box and how the box interacts with the rest of the world around it. This is a first step in deriving the ideal gas law that you might remember from chemistry, which says something about pressure and volume. So pressure is like how hard the stuff inside the box is pushing on the box. And volume, the size of the system, is related to nRT. That's like the number of molecules in the box. And then T is the energy of the things in the box. This is like very related to the ideal gas law. And we might see more closely how that's related to it later. All right, thanks.